This week's class, we're going to talk about math with water. So we're still talking about water, but we're going to be looking a bit more at the science of it and what we can do, what calculations we can do that might be relevant to you. So I'm going to cover the phases of water, key temperature points, how to convert between the temperature scales. We'll talk about pressure with water, and finally, volume expansion of water. Water phases, so there's three that we know: solid, liquid, gas, we talk about all the time. In solid form, water can be called ice. In liquid form, it's called water. And in gas, it can be vapor or steam. It can also exist as a plasma, which is when you take the gas state and you add heat or you add an electromagnetic field, and at that point you ionize the hydrogen and the oxygen molecules, and they have loose electrons. Water isn't usually one we worry about the plasma state with, but if you wanted to know what plasma looks like, you've got plasma TVs. If you have neon lights, the interior of the sun is plasma, and things like lightning and northern lights are also plasma. In that case, it's kind of the plasma of oxygen or nitrogen or the gases that make up air. Okay, so when we're looking at our physical states, when you are a solid, all the molecules, so let's say any sort of solid thing, are closely packed together, and they're always moving. Molecules are moving, but in a solid, they can only kind of vibrate. The more you add energy, like heat, the more they vibrate. But a solid has a set shape and volume, and you can't really change that. A liquid and liquid and gas are both fluids. Now, a liquid will take the shape of whatever container you pour it into. It will not escape out the top of the container, but it will take the shape. Gravity affects it. They are mostly incompressible. That means if you push on it, you're not going to squish the liquid, and it will in fact, that's really handy for hydraulics. We can transfer force using liquids because of that property. They also move around more so than solids, but not as much as gases, which take the shape of their container. They'll float at the top if they're not a heavy gas, if they're less dense in air. They are compressible. Okay, so when we change phases, that means we're going from different states of being. So the main ones we look at are here between solid and liquid, where you are either freezing in one direction or melting in the other. And likewise between liquid and gas, where we condense or vaporize. We're not going to look at recombination or ionization. We're not making plasma here, and very rarely do we deal with this kind of situation where you go directly from gas to solid, bypassing the liquid state. ASL means at sea level. So at sea level, the key temperature points are easy in degrees Celsius, which is our metric unit. So water melts or freezes at 0 degrees Celsius, and that's the phase between ice and water, liquid water. And it boils or condenses at 100 degrees Celsius, which is between steam and liquid water. If you take that over to degrees Fahrenheit, our melting or freezing point is 32 degrees Fahrenheit, and our boiling or condensing point is 212 degrees Fahrenheit. And when we make these changes, I mean, here I've said this is when we boil or we melt at different temperatures. As you increase the temperature by adding heat, that's when you change state, or you can also induce a change of state by changing the pressure in the system. So I know everyone probably will just do this on Google conversions, but you should know the math behind your conversions here. So TC means the temperature in Celsius, and TF means the temperature in Fahrenheit. So if I want to find a temperature in degrees Celsius, this is the formula I use. So if I am going to take this example, 5/9, and they leave it as a fraction because it's gross. When you do it, it's a gross decimal, so they like to leave it in fraction form. So when you do this, remember to respect order of operations. You have a set of brackets, so before you do any multiplying or dividing, I want to see that math in the brackets first. So I get 163 when I do the subtraction. And now because I've got this brackets smashed up, I get a instant fraction. We're just going to do this kind of math. And it doesn't matter what order you do it in, you will get the same answer anyway, and that should be 90.6 degrees Celsius. Going the other way, so if I start in Celsius and I want to make Fahrenheit, the formula looks similar, but the fraction has been inverted. There's plus instead of minus, and we drop the bracket, so respect that. So I'm going to put in this negative 25. Make sure you know how to type in a negative on your calculator. So this time I'm going to do all the math here first, because it's multiplication and division, which is more important than unprotected addition. So 9 times negative 25 divided by 5 should give you negative 45. There we go. And noticing that both scales have negative temperatures because they're relative temperature scales. In science, we often use Rankine or Kelvin, which start from absolute zero where there is no molecular motion, and they do not have negative values, but the Celsius and Fahrenheit scales both do. So we'll just do a couple more examples here. Number one, they want to make Celsius. So it's always when you see these, what do you want? It's the one on this side. So if you want to find Celsius, this is the formula you're going to use. You have that negative 32. And just remembering that two negatives make a more negative absolute value. And then when we do that math, 5 times negative 64 divided by 9, you should get something right here. Because when you're in those 30s, those negative 30s, that's where Celsius and Fahrenheit actually cross. Okay, looking at the second one, we want to find Fahrenheit. So this is the formula we use. And another shortcut you can do, 9 divided by 5 happens to be 1.8. So this time the decimal's nice, so you could kind of cheat and do this. It won't change anything. So you do the multiplication first, then you do the addition, and you should get 743 degrees Fahrenheit. Okay, so now we're going to talk about pressure, and we're going to talk about pressure applied to gases. So what is pressure? It's when you take a force and apply it over an area. So when you see things like PSI, pounds per square inch. Okay, so when you apply pressure to a gas, it's going to compress. The volume is going to go down. And there is a conversion between the metric unit, kilopascals, and the US customer unit, pounds per square inches, and it is 1 pound per square inch is equal to 6.89 kilopascals. So we'll use that as well. So when we talk about pressures, we have atmospheric pressure, and that's just if I'm standing here on Earth at sea level, there's a certain amount of air above me, and it has a weight, and it is pushing down on me with a certain pressure. And that is going to be 14.7 psi or 101.3 kilopascals, depending whether you're in the metric system or not. As I go higher above sea level, so if I climb a mountain, there's less air above me. I'm further up. So that means I would expect the atmospheric pressure to decrease and go down. And atmospheric pressure can also vary with weather. So when you have those cold fronts or storm systems coming in, your barometer changes, and that changes your atmospheric. That's a measure of the atmospheric pressure changing. Okay, when you take a gauge pressure, you are measuring the pressure of a gas within a container that it is pushing out on the walls of. So that's the most common one that you'd probably think of is when you take your tire pressure. That's a pressure inside the tire. Or if you're using kind of gases for welding or something you might do, then you have pressures in those tanks and you release them at a certain pressure. If you see PSIG, that just means pounds per square inch gauge. So that's just a way of recognizing that it's talking about the gauge pressure. So here's a little slide showing you a bit about how things look at different heights. So if you're at sea level, your pressure is 101.3 kilopascals. And if you're at Ottawa, which is a very little bit above sea level, you'll notice that I just went on a weather thing to find the data here, that these are very close to our normal atmospheric pressure, or the sea level one. And that's because we're really, relatively speaking, not very far above it. And as we move higher, you'll see that at the top of Mount Everest, you only have 31 kilopascals of pressure, atmospheric pressure. So that is a big difference. And that is very, very noticeable. And then when you get to the top of the atmosphere, when you're kind of moving into the vacuum of space, you have 0 kilopascals because you're coming across the atmosphere, you're coming outside of that. So there is no atmospheric pressure anymore. And kind of typical ones that you might find. How does this affect other things? Well, the higher you get, the lower the temperature you require to boil water, because you think about how those molecules are moving, and when we're at those higher elevations, like things are spaced out, there's less pressure on them, so the molecules are moving, so you're closer to kind of getting to that gaseous state from the liquid. So when you go to the top of Mount Everest, your water is going to boil at like 70 degrees Celsius instead of at 100. And same as you come down Kilimanjaro, we're at 80. If you go to Bolivia and you're in La Paz, you're going to boil at 87. If you're in London, you're close, so close, 14 meters above sea level. So essentially still boils at 100. And then if you start going down, I think Azerbaijan is where Baku is, and you're just a little bit below sea level. So it's going to take higher temperature there because the pressure is higher to overcome that and turn it into steam. And then if we go to the Dead Sea, which is the lowest point in the world, we're going to boil our water at 101.4. Okay, so absolute pressure. So absolute pressure is assuming that in a vacuum you have no pressure. So it's just a scale. It's like using a Kelvin scale instead of Celsius. It has an absolute 0 value, which happens to be in a vacuum. And then anything above that is good to go. So if you start at 0 psi here, you have that. So you have a certain amount of pressure that comes from atmospheric pressure. And then you have an additional amount of pressure that you measure on your gauge. And those two things added together are going to equal the absolute pressure. So there we go. So it is always, there's a formula, the atmospheric pressure plus what you measure on your gauge pressure. It can be a little bit confusing. And in US customary, if you see that PSIA, that means absolute pressure. Okay. And you use absolute pressure when you're doing gas law calculations, you're doing some chemistry. And for some reason, you guys need to know it as well. All right, so let's do a question looking at pressures. So here we're reading 34.5 on a gauge. So I know that my gauge pressure, and I'm just going to use 34.5 just so I know what I've got, and that's PSI. And I know that atmospheric pressure is 14.7 psi, and I want to find the absolute. So from the other page, there's going to be gauge plus atmospheric, 34.5 on the gauge, 14.7 in the atmosphere, and that will just add up to give not rocket science here, whoops, except for when I make the mistake of adding incorrectly, 49.2 psi. Okay, so this one, the second one, we're in metric in kilopascals, so I see the gauge pressure is what I'm looking for, and I have the absolute pressure is 438. We're at sea level, so that's telling me the atmospheric pressure is the standard one, which is 101.3 kilopascals. And those are all kilopascals as well. So this time, if I want gauge, I have to subtract the atmospheric pressure from the absolute pressure. we're going the other way. So we're going to take that 438, we're going to subtract 101.3, and we will get 336.7 kilopascals. So just knowing how to do that addition, subtraction, and which one to use where. So we're going to get into a bit of extra stuff, which is talking about the water pressure. So when I talk about hydrostatic water pressure, that is a pressure from water in a container. So we're thinking about things like, holding tanks, pipes, water towers. So this is a type of gauge pressure. We're not including the atmospheric pressure in this or any external pressure in this. So the formula is big P means pressure, and it's going to be in kilopascals for this one, and rho, which is this crazy wiggly P, is a density of water, and that's always going to equal 1 for our calculations. And G is the acceleration due to gravity. It's always going to equal 9.81 in our calculations. And H is going to be the height of water, and I want that in meters. So the only thing I need when we do these calculations, you're going to use 1 for rho for density, and you're going to use 9.81 for G. All I need you to put in is the height of water, keep it in meters, and it's going to spit out the pressure in kilopascals. And then if we need to go to pounds per square inch, we'll just convert afterwards, because otherwise numbers are much stranger if we're working in US customary. Okay, and just looking to this picture over on the right side, it doesn't matter what the shape of the container is or how much contact we have with the bottom or how wide it is at any point when we're doing that. It does not depend on that at all. Okay, so these are all going to have exactly the same pressure. Okay, so here we're going to look for pressure at the bottom of a tank if the height of water in it is 3.2 meters. And I don't care what the tank is shaped like, that does not matter. Okay, so we have P is what we're looking for, and it's going to be in kilopascals when we get the answer, because that's how it works. Our density of water is 1. Our acceleration due to gravity is 9.81. And our height must be in meters, which it is, so that's fine, 3.2 meters. The formula up in the blue box. So don't even have to write it, times 9.81 times 3.2. If I do that math, I should get somewhere around 31, and I'll keep a lot of decimals, kilopascal. Great, but I asked for PSI, so we need to convert. So you can either look at this and know that you're going to divide. If you're confused, use that kind of scale factor, where if I want to go set up those fractions and use the magic banana, 1 PSI equals 6.89 kilopascals. And I have kilopascals, so it goes on the kilopascal side, and I want to find PSI. And just remembering using this method where the two numbers that are kitty corner get to multiply, and the leftover one divides, kind of points you to that division. So I know that X is going to be 31.392 divided by 6.89, and it will equal 4.56 PSI. Done and done. Okay, moving water is interesting. We're not going to get into all the awesomeness of this, but there's something called Bernoulli's principle, and it tells you that the bigger your diameter is here, so if you have a bigger pipe, okay, with a greater diameter, it's going to be higher pressure and slowly moving, which might seem counterintuitive. And if you do a reduction in pipe size, what's going to happen is your velocity is going to increase. So it's going to go fast, but your pressure is going to drop, which, like I said, seems weird, but it's how it works. And then if you were to increase the size back up or even further, your velocity will slow down, and your speed, and then you will also have higher pressure return. Okay, so I guess you could think of it like on this side we have a higher pressure, and it's kind of pushing, we'll call that cross out the word airflow, pushing our water through the pipe, pushing it, making it go faster. And as it's racing through that fast part, the molecules are spreading apart and the pressure is getting lower because they're kind of running away in front of it. And then if you get back out, you can increase the pressure again. Like I said, it's counterintuitive, but it's super cool. And you use it for things like the Venturi effect. Like if you think about old carburetors where you would have a restricted flow where it's low pressure, fast moving air coming in, and in that carburetor you would be using that to draw the fuel into the place it needs to go. So terrible explanation, but that's what you're getting from me. Okay, so the next slide, I'm just going to try and quickly put this up, and this illustrates that kind of flow. So if you look to the left and to the right, you have these slower moving water pieces, let's say, and as they go through that restriction, they're accelerating and going more quickly. Looking at thermal expansion. So whenever you heat something, it gets bigger. And this is true of all substances, okay? Both solids and liquids. And whenever you cool something, it gets smaller. So think about a balloon. If you buy it in a store and you go out and it's cooler, you really notice this if you go out if below zero, suddenly your balloon is really tiny. And then if you get back into room temperature, it's going to grow again. So there's one exception to the contraction, and of course it's the one we're going to have to look at in a bit, but let's just work with this right now. So the idea is as you increase the temperature, add heat to the system, you're going to get those molecules vibrating faster and they're going to take up more space, okay, as they move and hit each other and bang around. And then as you lower the temperature, they're going to slow down and get tighter, closer together, take up less space. So these thermal expansion changes in size, they're relatively small. Liquid's much bigger change than you would get in a solid, but they are significant. And we have to kind of compensate. We use them and we compensate for them in our lives. So if you look at the first picture here, this is on a bridge, and you'll see this on every single bridge. It's an expansion joint. And that is because as the temperature changes, so as you get up to those 30-degree days or down to those negative 30-degree days, your bridge is actually going to expand and contract. So you need to leave enough space for that to happen, because if it wants to contract, or so rather expand, and it can't and it doesn't have anywhere to go, you're going to get cracking and buckling. The second picture is how we use this concept, shrink fitting. So if you want to fit something, notice they're heating something that needs to go with some kind of washer or something that needs to go on a shaft. They're going to heat it up and then they can slide it on. And then once it cools down, it's going to be a tight fit and you won't have to do anything else. And then we use this concept when we have our thermometers. So used to be mercury, now it's probably something else, but because volume expands, liquids expand when they get hot. If you have kind of measurements on your thermometer, as the temperature increases, you're able to accurately determine the change by looking at the volume expansion. And this speaks a bit to the shrink fitting thing. So this is something that people really don't like in my HVAC thing. So say this is a metal sheet and we have, drilled some holes in it. If I heat it, which means the entire sheet, the area will expand, will the holes get bigger or smaller when you heat it? So most people will say that the holes get smaller. They're thinking of it like baking a bagel or donut, like if you put it in, it's going to expand outward and it's going to expand inward. But actually that's not true. It's just like as if you photocopied it. So looking at those holes, as I get bigger, I don't know how much you'd have to heat it to change the size that much or what this substance would be, our holes get bigger. Okay, so it's more like zooming or blowing something up on a photocopier or a scanner than it is like baking. Okay, so just bear that in mind. And that's why that works for the shrink fitting, because they were heating something that had a hole in it so that the hole would get bigger and they could put it on the shaft and it would fit over. And then once it had cooled, it would be tight fit. Oop, there we go. Okay, So you can do expansion of solids in linear area and volume, but the one we're concerned about is volume expansion of liquids, and we're just going to look at water. Okay, so here's the formula. So we see triangle V. Triangle is delta. It just means change. So the triangle, it's one variable, there, change in V, delta V. Plain old V is the original volume, and this can be in any unit you want. Whatever you put into the equation is a unit you're going to get the change in. Okay, so if you have, I don't know, centimeters cubed going in, you're going to get centimeters cubed out. Okay, if you have liters going in, you're going to get liters out, so on and so forth. Okay, triangle T is one variable, so these triangles are not separate things. There it is. And for our sake, we're going to be like, it's always the difference between hot and cold. So you're always going to take your high temperature for me and subtract your cold temperature. Don't do it the other way and get a negative and then be like, well, this represents expansion or contraction. That does work, but it can be confusing. So just make a positive number and off you go. Okay. And the funny looking B, beta, is a coefficient of volume expansion. It depends on what type of liquid you have, because they all expand differently. It's a kind of part of their nature, right? Some things expand more than others. So it is unique to each liquid. We'll always give that to you. You don't have to figure that out or look it up or anything like that. And in fact, if you look it up, be careful because the units might be different than what I'm giving you. So look to the question, not to the internet. Now, before we go any further, I want to take a moment and talk about scientific notation, because this gets a lot of people missing marks. When you see this number, because your beta, this is the volume coefficient of volume expansion for water, happens to be this number. So if you're going to do some math with it, you have two choices. So you can move your decimal left or right, depending on whether the exponent is negative or positive, and this is the 4 is how many spots you're going to move it. So if I see negative 4 as the exponent, that means move the decimal 4 to the left. If it were to be positive 4, it didn't have a plus in front of it, it's just a number 4, that means move the decimal 4 right. So you can change the number right away before you use your calculation. So if I have 2.1 times 10 to the negative 4, I need to move, I'm going to change my pen here. My decimal place is 4 to the left, 1, and then just leave spaces, 2, 3, 4, and now you have your decimal place here. You fill in the missing spots with zeros, put it in front so it's clear. So that is equivalent to this number. 2.1 times 10 to the negative 4 is the same as this. Now, if it had been 2.1 to the positive 4, just making sure we see the difference, in that case, I would have taken it and moved my decimal 4 right. 1, 2, 3, 4. Here's my decimal place now. I fill it in, and that number is actually equivalent to with or without a comma. All right, so you can do that. Or your other option is that you can correctly enter the number on your calculator in scientific notation. So I want to go over how to do that quickly. So your button on, it's always different. It can be the EXP button. This is your scientific notation button. Here on this calculator, it's written like that. And on this third calculator, it's EE. I've seen all three of them. I think EXP is the most common. So if I want to enter 2.1 times 10 to the negative 4 on my calculator, I press 2 decimal spot 1. There's no, don't put the multiplication sign in. Don't put the number 10 in. This EXP button is replacing all of this. Okay, so there's no times 10, then exponent, because that will change your number and it will change your answer. Okay, and then you're going to hit either before or after, depending on your calculator, the negative sign. This might also look like this on your calculator, or it might be like this, but not the subtraction sign, the negative sign. So just kind of looking at these fuzzy picture calculators, I'm having trouble seeing it on any of them. That's nice. Okay, oh, here it is on this one. It's kind of brackets negative. Okay, and on this one, it's here. Okay, so that's how you make a negative. All right, so having said that, I think I will bring up my calculator if I can. Oh, no, it's not working for me. So I'm going to move on to the next thing, and then I will bring the calculator up and do it. Okay, so here's an example. I'm going to write down my formula. The change in volume is equal to the coefficient of volume expansion multiplied by the original volume multiplied by the change in temperature. Okay, so I'm going to list my variables because that's always smart. My original volume, looking at the question, is 250 liters. My coefficient of volume expansion is given to me 2.1 times 10 to the negative 4. And my change in temperature, always do hot minus cold. 40 subtract 15 equals 25 degrees Celsius. So if I want to figure this out, the math I'm going to do is here. And my answer will be in liters, and it will be the change. So just bringing up a scientific calculator to do this, I'm going to do my B, which is 2.1 exponent, and I'm going to try this button, negative 4. There we go. So that's at 2.1 times 10 to the negative 4. That's how it gets written in. Just walk away. And I need to multiply that by my original volume, which was 250. And I need to multiply that by, and you'll see in the top it's changed it to regular notation for me. That's fine. And then I need to multiply it by my change in temperature, which was 25. And there, that's my change in volume, 1.3125 liters. So I'm ready to bring that back to my slide now. And I know that the change in volume was and I've already forgotten it was 3125 liters. Okay, so I answered this question. What is the new volume of the water? So before you answer this, think about what you did. Did you heat it or cool it? I went from 15 to 40, so I was heating. If you are heating, you're going to add to find your new volume. It's going to be your original volume plus your change in volume. So we have to take that 250, we're going to add 1.3125, and we're going to end up with 251.3125 liters. So a little bit of change, but a change nonetheless. We're going to do a second example. Okay, so my original volume, just looking at the listed things, is 750 milliliters. That's fine. My change in temperature, always do hot minus cold, no matter which way it's doing. We'll deal with it later, which equals 82 degrees Celsius. And I was given the same thing for my coefficient of volume expansion, and here we go. Formula 2.1 times 10 to the negative 4 times 750 times 82. You're going to do that math, and it's going to come out to be 12.915. So a much bigger number than we had last time. How come? Well, our original volume was much higher. Sorry, milliliters, not liters, my bad. Our original volume, the number is much higher. Milliliters obviously are not as much as liters, but 750 is a much bigger number than 250. So that's part of the reason why. And also, our change in temperature was much bigger. We only changed by 25 degrees. This time we're changing by 82 degrees. Okay, so did I answer the question? No, because the question is, what is the new volume of water? So you need that second step. So you have to look at what happened. I went from 97 down to 15, so I was cooling. So this water is actually going to contract. So I expect my new volume to be my original volume. And I'm not going to add, I'm going to subtract because I'm changing by cooling, which is contraction. So 750 minus 12.915 And that should give you 737, and I'm going to round, 0.1 milliliters is a new volume. Okay. Okay. Water is a little bit strange. Something happens to water at a certain temperature that makes it unique. It makes it the reason that ice floats on water, which means that fish can live through the winter, and it has all kinds of amazing repercussions for life, but it is a little bit strange when we're doing these calculations, and it's a little bit annoying for you as plumbers. It'll be part of your job. Will come from the behavior of water. So here we have, in the first thing, I have a picture of a water molecule. And this is how it kind of arranges, and you end up with these kind of sides that are negative and positive. I don't need to get into the chemistry, but do remember that like things repel. So you never kind of have oxygen. If it's going to settle, water, if it's going to settle down and make a solid, it doesn't really want to be butt to butt, oxygen to oxygen. So it ends up forming this kind of lattice structure as it gets to the ice stage and just arranges itself in like these hexagons. And because of that, it takes up more volume when it's ice than it does when it's water. And likewise, as it gets to 4 degrees Celsius, it becomes the most dense. So it's kind of like behaving normally, right? Any other substance would be cooling, it'd be getting more dense, lower volume. But water suddenly gets its minimum volume is at 4 degrees, and then it gets bigger again. And that's kind of a weird situation. So let's look at the next slide because it has the actual volume one. So here's the change in volume. So as you come down to 4 degrees, you get to your minimum volume, and then suddenly the water starts getting a little bit bigger. It expands, okay, between 4 and 0 degrees. And when it hits this 0 degrees and changes to ice, it's going to line itself up in that kind of like hexagonal lattice, and it's going to get 9% bigger. So when water freezes, during the freezing process, it expands by 9%. So to look at this multiple choice question I just grabbed from somewhere, what happens as the temperature of water gradually increases from 0 to 15 degrees Celsius? It's actually going to, between 0 and 4, it's going to decrease in volume, right? To here. And then as you move from 4 to 15, it's going to increase in volume. So that is not normal. Everything else, as you cool it, it always decreases. But water will expand between 0 and 4 and expand when it freezes. So what does this mean for us? Here we have a pipe, okay? As the temperature decreases, your pipe is going to contract, and the cross-sectional area and therefore the radius and the diameter are going to get smaller, especially as you get below 0. And as the water freezes, as it gets to 4 degrees, it starts to expand a little. And then once it freezes, it expands by 9%. So to break them apart, so this water is going to freeze, and it's doing this. It's getting bigger. And your pipe is freezing and doing this, turning into an oval, apparently. And this is a very big exaggeration, but suddenly, come here. And it's going to go behind, but you're obviously going to see that your water is too big for your pipe. So what happens? You burst your copper pipes. So this unique behavior of water where it expands upon freezing and is less dense in its frozen form, lets ice float on water, but it also blows your pipes. And that's all we have to do for the rest of our water topic.